When I was choosing my college major, and seemingly at the time my life's career path, I knew one thing pretty clearly. I didn't want to be stuck behind a computer all day. I didn't want to be tapping away at spreadsheets and documents or writing code, not that I even really knew what that was at the time. I wanted to be out in the world doing real physical things. I also knew that I wanted to be doing something where I made things. I always loved thinking of something in my head and then making it materialize in the real world so it existed independent of myself and I could share it with others. So I chose the major that most closely aligned with these pretty vague concepts, the study of the biggest things that humans ever build, architecture. And for the next 5 years, I slaved away in studio, pulling all-nighters, making models and drawing with graphite on slide rules. But then, increasingly, after first year, ironically, I was sitting behind a computer, trying to wrangle two-dimensional lines to convey these large-scale, three-dimensional ideas that I had in my head. I found that during my 5 years in architecture school, the projects that I enjoyed the most were the ones where I was working on the final piece directly, not on models and drawings which were a proxy for an idea that would never actually materialize. Some of the projects that I liked the most were like this one up here, this copper chainmail jacket that I made out of 7,000 hand-turned rings, or this hobbit hole park bench that a couple of my architecture friends and I made. Then I knew that, oh, actually, let's go back one. I knew that a lot of my friends, when they were graduating, were continuing this trend of being CAD monkeys, drawing bathroom details and parking garages, when the real design decisions in buildings had been made sometimes years ago by the principals of the firm, mostly in their 50s and 60s. I felt trapped on the one hand by my strong desire to want to make physical objects, and on the other hand, my understanding that physical objects are expensive, and usually, by the time that they go from concept to construction, they've been compromised by running the gauntlet of client demands, budgets, physics, building codes, and 1,000 other things, so that by the time they're actually constructed, they end up looking very similar to most other buildings out there. Then in 2012, I saw a glimpse of the future. I saw two videos that would end up changing my life completely. One was the Oculus Kickstarter video, and the other one was the first Leap Motion demo. I remember showing both of these videos to anybody who would watch them, rambling on about how if these technologies were real, if they weren't just gimmicks, then we were about to have Matrix-like technology in our lifetimes. We were about to be able to step into virtual worlds and experience them and interact with them the same way we experience and interact with the real world. I would tell my architecture friends that computing is about to become spatial, and most of them would kind of just nod and say, yeah, I'm sure that'll be cool. It wasn't up until when I got my DK1 about a year later that they started understanding what I meant. Then when I got my DK2, which came with a positional camera, that completely changed everything. And then about a month later, I got Leap Motion, which changed everything again. Originally, I was just a zealous virtual reality enthusiast, showing people every demo that I could possibly try. But then eventually, on evenings and weekends, watching YouTube tutorials, I started learning Unity and started making things. They were digital things, yes, but they didn't feel digital anymore. They didn't feel physical either, but at the very least, they felt spatial. They started to feel volumetric. And I would model something on my screen, but it no longer was bound to the two-dimensional plane. I could put on a headset and I could walk around these objects and experience them visually the same way that I would experience any other physical object, with 3D stereo depth and parallax. From a visual perceptual level, they were the exact same as any other physical object in my room. Then, amazingly, I could reach out and poke the objects, and they would react exactly the same way as a real physical object. In terms of these two senses, physical objects and digital objects had started to blur together. And spaces. I could imagine a space and then 3D model it, and then a moment later put on a headset and experience it the exact same way I would experience a built space. I would crane my neck to look up at a cavernous spinning space station that had existed in my imagination only moments before. In terms of visual perception, modeling something on a 2D screen and the spatial experience that it was trying to convey were now one and the same. And so for the last 2 years, that's what I've been doing as a virtual reality designer, developer, and evangelist at Leap Motion, where we're working on technology that brings your hands into virtual reality directly, without the intermediary of controllers or gloves. You can reach out and interact with these virtual objects the same way that you've reached out and interacted with physical objects your entire life. Making these digital experiences that feel spatial and strangely physical because you're using your hands directly is something that I think is profoundly amazing, and I've gotten to share this magic technology with hundreds of people at this point. And we're only scratching the surface at the moment. Virtual reality, augmented reality, and mixed reality are a combination of many, many different disciplines. When you put on a headset, you're hijacking someone's perceptual system. You're either simulating, augmenting, or mixing our reality with a completely synthetic designed one. I think we're going to be learning from other fields and incorporating lessons into virtual reality, augmented reality, and mixed reality for a really long time. And with a title like Spatial Computing and Your Body, the Interface, I could spend 50 minutes talking about any one of these aspects, the social aspect or the neuroscience aspect. But today I want to focus on the merging of two worlds which I have felt have always been sort of polar opposites. On the one hand, the long history of humans shaping and molding the world into form and space to serve their needs. And on the other hand, the relatively short but equally important history of the digital world, which has been empowering us and connecting us increasingly over the last 40 years, and today permeates pretty much every aspect of our daily lives. As the mobile computing paradigm that we're in today has been defined by our ability to take our devices with us as we move around, I think the spatial computing paradigm that we're moving into is going to be defined by the use of the space around us as a medium to interact with technology. And space is the native medium of human interaction. Biologically, we've evolved as creatures operating in a three-dimensional world who channel information in from our senses to create mental spatial models, which help us make sense of where we are, where other things are, where we want to go, and how to get there. And technologies which, in some sense, tap into this innate human ability to create mental spatial models are easier to learn and more efficient to use because they rely on an inbuilt ability that we all have. They require less cognitive load from the user. Robert Scoble and Shel Israel, in their book, The Fourth Transformation, lay out consumer computing paradigms as having gone through 3 transformations so far. At first, computers were only used for specific data storage operations, and specially trained employees interacted with them by feeding them punch cards or magnetic tapes, which either had holes at a certain position or didn't. Then in the 1970s, the first transformation happened with text input and keyboards, which allowed people to press buttons to directly input text to communicate with computers using words. Then in the 1980s, the second transformation happened with the introduction of the graphical user interface and windows, icons, menus, and pointers combined with mouse input. This allowed far more people to use computers in their daily work. Then, around 2007, with the introduction of the iPhone, we ushered in the third transformation, which was marked by portable computers that we carry around in our pockets, where we use our fingers to interact with the screen directly. Touchscreens brought us a huge step closer to minimizing abstraction in computing, letting us glimpse for the first time what it's like to physically manipulate digital objects. Touchscreens on smartphones and tablets have greatly increased the accessibility of computers, so that even technologically averse grandparents who might have hated using a mouse could now swipe through a digital photo album as easily as they would swipe through a physical photo album. And I'm sure a familiar sight to everyone is kids, some too young to even speak, at airports or doctor's offices, tapping and swiping away on touchpads and getting enough feedback from their interactions to have a meaningful experience. In some 40 years, we've gone from needing special training to learn the abstract language of computers in order to be able to interact with them, to interfaces that your grandparents or a toddler can just pick up and use. And we're even seeing that on two-dimensional screens, on touchscreens especially, people are using interfaces that are trying to use spatial models within the limits of 2D. On the left here, where the video is not playing, you can see an example of floating dimensionality, where an app arranges events like cards that you flip between. This is a really popular paradigm, especially in dating apps, where people are represented as cards that you swipe between. And then on the right here is something called Bump Top, which is an approach that Google brought out in 2010, which tries to bring physics into the mix to make your digital desktop feel more like your physical desktop, with all the nuances of physical interactions between objects that you would place on your real desktop. Now in 2017, we're undergoing the fourth computing transformation, with virtual reality, augmented reality, and mixed reality leading the transformation into spatial computing. And as we've seen with each previous transformation, as the output transforms from screens in our pockets to wearable devices that we wear on our heads that project 3D images into our eyes, so too will the primary input transform. The thing that we will use to interact with these new spatial outputs, its other half, is spatial input from our bodies. As the keyboard was to text input, as the mouse was to windows, icons, menus, and pointers, and as our fingers are to the touchscreens in our pockets, so too are our bodies to the space around us. They are the interface through which we interact with the real world, and so clearly they will be the interface through which we interact with tomorrow's spatial computing platforms. During this fourth transformation, I think we're going to see a lot more sensors that track our bodies at much higher fidelities than we've ever seen before. From hand tracking to eye tracking to voice tracking to face tracking to body tracking to heart rate tracking to brainwave tracking, our physical bodies are capable of a very wide spectrum of interactions. From incredibly subtle ones like the saccadic movement of our eyes to really intense, fully engaged ones like when we're playing a sport that takes our whole attention. But when we look back at input throughout consumer computing so far, text input, mouse input, and touchscreen input, we can see that each is primarily binary. We're either pressing a button, clicking a mouse, or touching a screen, or we're not, regardless of how we're doing it. This binary state of pressed or not pressed can be combined with multiple buttons or fingers, duration, how long we're doing it, and in the case of mice and touchscreens, how that point is moving in 2D space. Now, as a relatively new student of human-computer interaction when I started at LeapMotion, when I began researching the history of 3D input in computing, I found that the field was almost as old as computing itself. Researchers have been using optical, magnetic, ultrasound, mechanical, and hybrid systems to bring 3D input to computers for decades. But up until now, most of these instruments have remained in the domain of research labs or medical and engineering applications which are really specialized, failing to break into mainstream computing. Today, because of the rise of spatial computing as a true 3D output, and the resulting market demand for a complementary, suitable 3D input, combined with advances in cameras, lasers, computer vision, machine learning, and a host of other fields, we're seeing systems capable of tracking a three-dimensional point in space at incredibly high accuracy with incredibly low latency at consumer prices. Two examples that I'm sure we're all familiar with are the Vive's Lighthouse system and Oculus's Constellation system. These systems combine the instrument input of button presses and swipes with three-dimensional tracking of a point in space. And looking out a few years into the future, for home gaming and entertainment use, for enterprise use, for arcades and other specific location-locked use cases where immersion is the goal, these systems will continue to provide reliable 3D input using external computers and external sensors to track controllers, tracking pucks, or other wearable markers, but at the cost of a lack of mobility. For mass mainstream adoption of spatial computing platforms, especially augmented reality, which will all be mobile, the form factor of these devices will have to shrink, and they'll have to become all-in-one devices, capable of not just tracking objects manipulated by our bodies, but our bodies themselves directly. The first of these devices, like Microsoft's HoloLens and the ODG R9, are already on the market today. And there are many, many, many more that are on the way, like Magic Leap's product, maybe. You can see that these touchless sensing technologies are already pretty advanced today. This is a clip from a demo I finished like a week ago called Mirrors, which focused on body presence and the rich, expressive communication that's possible when you track your hands skeletally as 26 data points. So at Leap Motion, we don't just track your hand as a point cloud or as a height map or anything like that. We track your hands as a full skeleton with 26 data points representing each joint in your finger. So it's your complete skeleton volumetrically brought into the digital world with you. And you can see the fidelity at which we're tracking your hands allows you to express your movements in a way that you just could not do with a controller. It's a human body in virtual space creating expressive effects. And once we know the position of your hands, we're able to let you interact with virtual objects in these incredibly nuanced physical ways. This demo is another one I made called Geometric, which focused on rigid body interactions at finger scale. When I put people into this demo for the first time, usually they start out by smacking the objects around with massive motions of their arms. I think that's because people are used to motion tracking, meaning this very macro level of tracking, like maybe with a Kinect or another system, where your body is represented by big points like this. So you have to make these huge gestures for it to actually register. But after a minute or so, most people figure out that they aren't just these big skeletons of tracking points. They have 26 of them in their hand. So they can poke and tap and flick and interact with objects like they do in the real world. And I found most people play around as though they're rediscovering their hands and rediscovering physics, because in a sense they are, just in virtual space. And hand tracking is just the beginning. Eye tracking is going to offer an even more subtle level of interactions, ones which we're usually not even consciously aware of. And eyes and hands are how we interact with most things every day. So I think in the next generation, or maybe the generation after that, eye tracking and hand tracking are going to become standard across all headsets. And we'll look back and think, how did we ever not have those things? Kind of how we look back now at the DK1 and say, how did we ever do without positional tracking? Similarly, face tracking is already pretty advanced using just the monoscopic camera on your phone, as you can see from this example from Snapchat. And that's going to bring even more information from our bodies into these spatial computing platforms. And I'm sure in a couple of years, more things like heart rates, brain waves, all of these things will be used to bring more of ourselves into virtual spaces so that they react and interact on a deeper level. But back to today. So computing is about to become more accessible than ever, engaging us fully as three-dimensional humans for the first time. And as we saw with the rise of graphical user interfaces and touchscreens, that has a relatively short history and has drawn deeply from the much longer histories of fields like graphic design, typography, and motion graphics. We've also seen that people who, over the last 10, 15 years, who might have traditionally gone into one of these fields, going into two-dimensional user interface design on web, mobile, and desktop. And I think we're going to see a similar migration of people who, like myself, might have gone into architecture, industrial design, or set design, moving into virtual design for spatial computing, and for a number of reasons. In spatial computing, traditionally, as a 3D designer, having tons of conceptual ideas, usually only 0.001% of those ideas actually make it into the real world, as like I said before, building physical spaces and physical objects is an expensive endeavor. And usually the things that get built, maybe only 30% of the original idea remains intact as it runs through the gauntlet of physics and budgets and clients and building codes and on and on. But now in spatial computing design, you can go from a concept to having your space or object experienced by an end user at one-to-one scale without any middlemen. No client demands, no budgets. The only cost is how long it takes you to 3D model the experience. Another factor which I think is going to lead to a lot of 3D designers moving from traditional roles to spatial computing design is the crazy increase in the tools that we're going to be using. So on the left here is an example, as a sci-fi short from 2009 called World Builder that I remember watching at 3 a.m. in studio with some of my architecture friends and musing about how amazing it would be if this was actually how we got to design buildings. And then we closed that window and we went back to our desks with our laptops and our mice and our cans of Red Bull and went back to clicking in CAD. And then on the right, you can see an example from Unreal Engine 4's InVR editor from this year. And they're pretty much the same thing. We have the dream tools that we've always wanted available to us now. So in addition, looking at 3D design for humans, as I think there are a lot of people who are going to be moving from physical fields like architecture, industrial design, and set design into spatial computing, and like myself, we have a lot to learn about computer graphics, rendering pipelines, shaders, and on. I think it's helpful for those of us who are more on the software engineering side of things to learn a little bit about some of the core ideas in the history of 3D design for humans. So let me attempt to give a very brief and entirely subjective look at some of the core ideas in the history of architecture and industrial design. So from Neolithic architecture and the forging of stone tools, we've been designing 3D spaces and objects for humans to use for thousands of years. And while architecture and industrial design have been used in games, 3D games, for a few decades now, they've mainly been used as backdrops and props for nav meshes or platformers, where the real meat of the experience is the gameplay, which is mediated through buttons on gamepads. When most people think about architecture, they think about an iconic style or a building, materials or structures, maybe even an architect themselves. And while all of these things are necessary components of architecture, the core thing, the reason for it all, is to define space. Because it is not the concrete or the bricks or the glass or the steel or the wood in a building that we as humans can actually occupy and use. It is the space that those things define. And these spaces can take many forms, from small to large, from well-defined to blurry and free-flowing, from brutally indifferent to warmly inviting. Architecture is the study of how humans perceive and experience space, and how the design of spaces can fulfill specific needs. And the experience of a space can be affected by many, many things. Starting with a completely blank, featureless void, anything that's added is going to have an effect on how that space feels. So it can be helpful to think about what the intent of any addition actually is. So a couple of core architectural concepts that I think spatial designers of the future are going to be doing well if they consider are form and space. Two sides of the same coin. Form defines space, and space defines form. One cannot exist without the other. By defining mass, you are also directly defining void. And interestingly, in virtual architecture, the mass isn't even solid. It's geometry with textures applied to it. If you wanted to, you could stick your head through the geometry and you'd see the other side. But visually, they hold the same weight. And actually, there's some cool stuff from Colin Northway and Kabibo where you put your head through a space and there's like a whole other dimension on that side. But we'll get to that a bit later. Light. So the only way that we actually perceive spaces are by the light that bounces around the space and then enters our eyes. Therefore, the same space can feel dramatically different under different lighting conditions. In physical architecture, working with light is this natural light, is this rigidly predictable thing. We know where the sun's going to rise, where it's going to set, and how it's going to move through the sky. So we have to design our spaces in such a way and orientation to take advantage of this rigid predictability. In virtual architecture, we have complete control over the lighting, even able to change it at will. In geometric, that demo I showed before, the sun rises and sets in 3 minutes. And so with the dynamic GI in Unity, you get these shadows that move much faster than they would in the real world. We can even create lighting situations that would cost millions of dollars to do in the real world, or might not even be possible given physics. I think this is going to be a really huge thing in virtual architecture design, to draw users' attention, to create spectacles that you could never see in the real world. And I think it's going to be used extensively. Scale. So humans are usually around 5 to 7 feet. So spaces can either acknowledge that scale by sizing elements that are suitable for people, like in this example, where the benches all seem to fit people, windows are at eye level, so that they reference people, or, on the other hand, a space can be completely indifferent to the size of an individual, making a feeling of monumentality, and as though any individual doesn't really matter that much. As an in-between, this is a proposal in New York that just got approved for this like 10-story structure that's massive, but it's made of staircases, which are all sized based on the stepping height of a human. So although it feels massive, it also feels inviting for humans because it's built entirely out of blocks that are sized for human scale. Organization. The organization of a space will either balance it or give importance to certain areas while making other areas feel secondary. There are many ways to do this, from alignments or disruptions along an axis or a datum to differences in size, orientation, and location. Similarly, organization can imply movement and direction through the use of repetition and rhythm, helping someone understand how they can enter a space, move through it, and exit it just through the forms. And lastly, the materials used to define a space can have a massive impact on how it feels. Wood can make a space feel warm and inviting, closer to nature, while glass and steel are thin and strong, creating a light, airy feeling. On the other hand, poured concrete or stone implies a sense of stability and mass. Virtual architecture materiality is a really interesting concept because, again, it's geometry with textures, and even if you have crazy good PBR from Substance Designer, it's still just geometry with textures over the top. But visually, because we have these strong associations with materials, they have the same effect on us as though they were real solid materials. But I think we're also going to see some really cool virtually native materials that take advantage of things that you could not do in the real world. And I'll show a couple of those at the end of the presentation. Now, in terms of 3D object design, we've all heard the modernist mantra that form should follow function. That is, the design of an object should be derived from its purpose. For example, a spoon is a handheld tool for scooping and stirring. Physical functions like scooping and stirring, cutting, shading, connecting, pushing, pulling, they serve as really solid foundations for the design of an object's form. And when you factor in physical constraints like bending stress or tension, shear, torsion, you can get a pretty good filter to narrow down, for example, how thick a plastic spoon's handle should be to avoid snapping when it's scooping something. Similarly, ergonomics, our understanding of the human body and how to optimize its interactions with other parts of a system, give us another good filter to narrow down an object's form. A spoon's handle has a direct relationship to the shape of a grasping human hand, because in order to fulfill its function, it needs to be comfortable to hold. These three filters, how an object can best serve a physical function under physical constraints held by a human body, have been the driving force behind most of the objects that we interact with every day. They've been an unquestioned driving principle behind all object design since we were sharpening sticks and rocks thousands of years ago. And it can be tempting to want to copy these familiar forms from the real world directly into the virtual space. Skeuomorphism, this idea of using symbols from the real world to denote digital versions of those objects, can be a really powerful tool in a virtual designer's arsenal. The idea of skeuomorphism has been used as a crutch for almost every new technology, especially during the last two computing transformations, as a way of onboarding new users. You might remember when we talked about digital desktops, this metaphor of a digital desktop has stuck around for some 30 years, and we basically use the same framework today. And you might remember when the iPhone was introduced and iOS was introduced, it looked way more skeuomorphic with leather indents in the top or books which actually sat on bookshelves. And the only reason that today Apple can do away with that is because we've been trained over the last 10 years to work touchscreens. And today we can see a perfect example of skeuomorphism alive and well in Alchemy Lab's job simulator. Admittedly, the entire premise of the experience is to simulate in a cartoony video game way real environments and props. And it works incredibly well as a first-time experience for new users of VR. Once they've figured out how to use the trigger on the Vive controllers, place it in an object's trigger zone, press the button, and now you're holding that object, they don't need to be told how to use the phone in the office level. There's no button combination, no swiping. They just walk over, pick up the phone, and hold it to their ear exactly the same way that they've done hundreds of times before. However, despite the advantage of instant familiarity, when skeuomorphism is used as a primary design methodology, it's limiting. Even in VR, where we can recreate an object in full 3D, when understood in reference to real-world objects, virtual objects will never be able to meet all of the expectations that users have. A perfect example is one of the developers at Alchemy Labs, Devin Reimer, talked about how creating the liquid systems in Job Simulator took 500 hours. And that was, to make liquids, hot and cold liquids mixed together, to make colored liquids mixed together, to allow users to slosh them around a cup, just to meet the minimum believability levels for a cartoony video game version of these things. And Alex Schwartz, the CEO of Alchemy Labs, said that watching playtesters do a thing that they expect to work in the real world and then seeing that it doesn't, that's how our to-do list fills up. Using purely skeuomorphic design in VR casts the real world as this unattainable and unnecessary reference point for a medium with far more to offer. Also, the physical functions and physical constraints that have defined the forms in the history of architecture and industrial design are no longer factors in virtual space. For example, a spoon. In a virtual application, a 3D model of a spoon doesn't do anything. Its form, its geometry, is completely separate from its function, which is driven by code. Anything that the spoon can do has to be written and specified into the program. And for the example of using a spoon to stir a liquid, even with the incredible 3D physics simulations that we have today in 3D game engines, unless the central premise of the application was VR spoon stirring, it would take far too much processing power to simulate that realistically. Ergonomics, too, in virtual space design doesn't really mean the same thing. If you're tracking the human hand, until we have crazy exoskeletons that everyone's somehow okay with walking around wearing, when you grab a virtual sphere, your hand's not going to stop at the perimeter of that object. It's going to penetrate it to some degree. And I think we're going to see a lot of interesting, again, virtual materialities where as you close your hand, the object deforms so that it forms around the pose that you have. And I'll have another example of that at the end of the presentation. But one very important aspect of these real-world physical forms that we should not ignore are affordances. Affordances are the possibility of an action upon an item that is communicated to a user by aspects of its shape. For instance, a button with a rounded top affords the action of pushing it down, or the switch on a toggle affords the action of flipping it. These visual cues, even on virtual objects, give users an anchor from which to begin an interaction. The challenge is to make users feel familiar in a new environment, for interactions to feel intuitive, but then to flip the expected, to create something new and let them do something that they could only do in virtual reality, something that could never happen in the real world. It's a really difficult thing to do well, but I think we're already seeing some amazing new design trends and typologies emerging. For example, dynamic scaling. So on the left here is a demo called Titans of Space. That was my very first ever VR demo when I got my DK1, and it'll always hold a special place in my heart. And when you start, there's the Earth in front of you at a millionth scale, and then the sun appears, and it's massive. It's the biggest thing you've ever seen. And then Rigel appears behind it, and it's even bigger. And continually, they just scale these things up, and every time you're like, that is the biggest thing I've ever seen. On the right is a demo called Neos the Universe, which takes the Eames Power of 10 video and brings it into VR. And the reason that these things are so effective is because when you're experiencing them in a headset at one-to-one scale, you know how big your body is. If you see this on a screen, it doesn't look that impressive. But if you put on a headset and see it, because of the reference point of your own body, the dynamic scaling is just this crazy new experience. Similarly, playing with scale. So on the left here is Iris VR, an architecture virtual reality program, where you're looking at a model of Villa Savoye, and you can just shrink down immediately, and you're inside it. It gives you this understanding of the gestalt of the design, and then how it feels to actually be inside it. On the right is a demo called Metacloth by Kabibo, where you're editing this little maquette of this liquid metal landscape that forms around you as you're interacting with it, giving you this duality of a sense of scale that you could never have experienced before. Another idea is this dynamic spaces. So on the left here is a demo called Grid Moon, where instead of teleporting, when you point at a space and click the trackpad, that space reforms dynamically around you, moving you essentially to that space. On the right is a similar idea from an architecture program. Impossible spaces. So like we saw in Mary Poppins or Bruce Almighty or Doctor Who or whatever your reference is, the idea of spaces which are seemingly overlaid on top of each other, portals that you can move through, or drawers which are bigger on the inside than they are on the outside. These crazy ideas which seem intuitive but also magical and unexplainable, that's the kind of stuff that I think we're going to see stick in virtual spaces. Another idea, objects that become spaces. So on the left is a demo called World of Comenius, where you have these spheres, and you can see the space that they represent, and when you tap them, that space envelops you, and suddenly you're inside that space. On the right is an aspect from the Wave VR, which just came out and is amazing. You should try it. The idea of a social space that you invite someone to. So you offer them this bubble, and when they accept, that bubble takes both of you into a space where only you two are. I think Kabiba worked on that one as well. Object non-permanence. So we all know that when you look at an object, a big object, and then you turn away, just because you don't see that object doesn't mean that it's not there anymore. We learn that pretty quickly when we're 2, 3 years old. This demo called Sightline the Chair, which was one of the pivotal demos of the DK2 era, flips that on its head. So when you look away and then you look back, the world changes. And that's the main mechanic. You just keep doing that and it keeps happening, and every time it's magic. Infinite inventories. In Fantastic Contraption, they have this mechanic of an infinite backpack where you are pulling out struts to build your contraption. And on the right, you can see a more traditional example from a menu where you pull out pieces, as many of them as you want. I love the backpack example, though, because that's just cool. Holographic interfaces. So in Tilt Brush, you have this palette, which is like a carousel of 2D menus. That has some 3D to it, has depth, but it's still pretty much sort of a Windows icons, menus, and pointers style interface. On the right is an example from Cosmic Trip, where you can summon a menu and then hit physical buttons to control your actions on it. And it feels like a real physical control panel that pops up when you need it and then goes away when you don't. And the slide that I just showed, where we were looking at the history of 3D input and instruments, now that we're tracking your hands in 3D space at a really high fidelity, we can create virtual instruments that we can use to give us 3D input in our spatial computing applications. So this is another demo I made called the Weightless Training Room, where the idea is that you have these projectiles and you have these spinning targets that you have to try to hit. And you can grab the projectiles and you can throw them, but then once you throw them, you can pinch in the air and drag, and this sphere UI pops up. And the vector that you have from your pinch point to where you're dragging gets added as thrust to the projectile, so you can control it in midair. And I think we're going to see a lot of these sort of virtual 3D input instruments, because instead of spending a ton of money prototyping, building, manufacturing, you can just write some code and see if it works or not, and have it be a very specific use case for it. Another trend that we've seen emerging at Leap Motion is the idea of virtual wearables. So if you've got your hands in virtual reality with you, if you have actions that you want to be using often, it makes sense to just attach them to your arms, the same way you would attach a smartwatch today. When you flip your hand over, maybe you get more options, you can interact with them, and then when you flip your hands back over, they go away. I think we're going to see even more of these sorts of wearable virtual interfaces as more people enter spatial computing design. And then lastly, virtual materiality. And this is one of my favorite sort of ideas to explore. Wish the videos would be playing. Maybe they will. Nope. Okay, we'll just go without the videos. So on the left, in the video that you can't see, is a demo I made called Mr. Material, which focused on the idea of virtual materialities. So that little ball there, when you grab it, it doesn't just stay static. It knows the position of your fingertips, and it deforms so that however you're holding it, it still makes sense. You can poke it and feel it, and though you aren't actually touching anything in the real world, you're just waving your hands in the air, because of the visual feedback, because of stereo depth and parallax, and because of audio cues, it can trick your mind into thinking that you are having a haptic feedback response. Similarly, on the right, another demo from Kabibo, who used to work at Leap Motion. This is Rainbow Membrane, where you're in a room that seems to be made out of liquid iridescent metal. And as you touch the walls, everything reacts and jiggles, and it's one of the most satisfying VR experiences I've ever tried. So, spatial computing and the use of your body as an interface for it represents what I think is the greatest design opportunity in history. It is the convergence of our understanding of space and form in relation to the human body, combined with the magic and infinite potential of synthetic designed digital experiences. We're moving into a future where we're actually going to be spending less time stuck behind a computer screen and more time standing up, using our bodies the way that they were evolved to be used. I don't think anyone has a clear idea of how these systems, spaces, and pseudo-objects are going to evolve, but I think that's one of the most exciting aspects about it all. And I hope this talk has made you feel even a little bit of that. Thanks.